Alright, welcome back. We're going to look at Laplace equation now. This is the last topic we're going to cover in PDEs. Well, I might do some other small things a little bit after Laplace, maybe. But we're going to look at Laplace equation over a rectangular domain. So what Laplace equation is 2D. Well, it doesn't have to. It could be 3D too. Any of the ones we've done could be 3D, but it's 2D, steady, meaning no time change. It's time independent. It can model heat transfer, wave propagation, any sort of potential, electric potential, wave potential, fluid potential, you name it. That's why it's often called the potential equation. You might hear it referred to as so. But what is the Laplace equation? Well, it's 2D and it's time independent, so all it is just the solution in x plus the solution in y equals 0. Now this is the homogeneous case, of course. If we had any external factors, they would go over here, you know. But we're just going to look at the homogeneous case, of course. We have no external factors applying to this. Now, keep in mind, this equation only works, this solution only works for time-independent situations. You cannot model time-dependent situations with this equation. I think when that occurs, don't quote me if I'm wrong, but it might get too complex, where you introduce nonlinearities. So this might be the limit of Laplace's equation, is time independent. Don't quote me on that. Not sure. That's just my guess. That's why this is taught, but this is still a pretty hard section to get through. This is going to be a large section. A lot of examples we're going to go through, because there's a lot of different kind of situations you can encounter. So Laplace equation. Laplace's equation. Laplace equation, whatever, is this. We're going to be looking at a rectangular boundary. This is x, this is y. And we have our rectangle. We're going, x varies for this particular problem, x goes from 0 to a, y goes from 0 to b. We have, you notice, we're only given boundary conditions. And yes, because do you see any, well, because we're time independent, right? So we're not going to have any initial conditions that's depending on time. We have 4 boundaries, so we have 4 boundary conditions, and that's it. We are actually going to use, well, you'll see how, I'll go through it, you'll see how it works. I don't want to overload your brain in the beginning. Let's write down our boundary conditions here. Draw them on our rectangle. So we have u 0, y equals 0. This tells us that at x equals 0 along y, the solution, whatever quantity, is 0. It could be whatever. You can imagine this is heat transfer. Imagine we're doing 2D steady heat transfer. Temperature, or the heat, is 0. On that boundary, UAY is 0. That's over here. At A along Y. My U looked awfully like an A there. Okay, we have UXB equals G of X. Right, because at B along X. We have at 0 along x is 0. Okay, that's the boundary conditions. You're thinking, how the heck do we solve this? Because we have 4 boundary conditions. Why don't we just have 2? Well, I'll show you how to solve it. It's actually not too bad. Let's go ahead and separate the variables. Remember, still the same steps. Step 1, separate variables. equals 0. Remember, we're going to define our u, let me put this in parentheses, u of xy is equal to x, I'll use y, I guess, y, little y. For my capital Y, I'm going to draw it like this, probably. No, that looks bad. Let's try and make it straight. I don't know how to draw capital Y's. Knowing this, we can replace these. We know how to separate the variables, right? It's supposed to be a big Y. I cannot draw that. Oh man. Okay. That does not look like a Y, does it? Yeah, so then we have x double prime. I'm sorry if I write down lowercase y. I can't do an uppercase. We have x double prime over x equals separation constant. I'm still using positive lambda, just like before. You may see professor use a different one. It doesn't matter. You get the same answer as long as you're consistent throughout your boundary value problem. You will get the same answer. Your boundary value problem will be different though, just so you know. We're going to have our two ODEs. And now you're thinking, well, this is interesting. This is very interesting. We have 4 boundary conditions, 2 ODEs. It can kind of be inferred that we have 2 boundary conditions per ODE. Well, currently we have 3 that are 0, so we have x of 0 is 0. We have y of 0 is 0, and we have what is that? What do I have written on my notes? Oh, I'm looking at a different problem, sorry. X of a is 0. So, boundary value problem. Well, we don't use this one for the boundary value problem. We use these two for the boundary value problem. We're going to stick to solving. I mean, you have to do this one because we have... So the reason why... so, you know how I've always had one initial condition? You can kind of think about this being our initial condition, kind of treat it the same way. This one here, kind of treat this as our initial condition, even though it's really not. But just treat it as an initial condition. It's the same process. This one here is going to be used, this one here, to solve for y, which I'll show you in a moment. But let's do a boundary value problem. We have these two values here. And our equation here. So we have lambda equals mu squared x double prime minus mu squared x equals 0. X is equal to plus minus mu. R is equal to oh wait. Plus minus mu, right? So you go up to here, you're gonna get this. These are little x's, by the way. Little x. That's negative. Now, we know from experience that for this case, when we have Dirichlet boundary conditions just from doing this so much. We have so much experience at this point now that we know this is going to be trivial. Right? I mean, it's only trivial. It's very important to write that down. Only trivial. Right? We know this. It's Dirichlet. I don't know how to say that word, but non-derivative boundary conditions. It's always going to be this case. The only case for Dirichlet boundary conditions, we've done this a million times already, is for lambda less than 0. We know this. When lambda is equal to 0, we know, this is an easy one to do though, but we know it's going to end up like that. This becomes our reduction of order case. We know this is going to be trivial as well, because we've done it so many times. So let's go down to our last case. If you don't know how to do boundary value problems by now, I recommend going back to learning how to do those. I'm actually going to do this one out because I know this is going to lead us to a solution. Right, let me write it out. X double prime is equal to negative. Yeah, this will be complex. Has to be. Solve the characteristic equation. Square root. Use a shortcut for complex roots. Cosine mu x. Mu x plus c2. For some reason in my notes I use y here. That's not right. I don't know why I was doing that. Sine mu. Oh no. Mu x. No, I can't draw mu's. Okay. First boundary condition. C1 equals 0. So then we're left with this. X. I keep looking at my notes almost writing down a y. Next boundary condition. X of L. Oh wait. A is the length of that side. Excuse me. We have C2 sine A. And now we know from experience how to do this. We set, remember we want to figure out what sine of this is 0. In order for that to be 0, this has to be some value of n pi. So then mu is n pi over A. Our eigenvalue is going to be negative n squared, pi squared over A squared, because it's negative mu squared. Our eigenfunction, C of n sine n pi over A times x. Yep, I use this right here. Okay. Let me just box those up. I don't need that. Beautiful. We're only at 15 minutes. Okay. That's good. This is where things change. Well, I guess things technically did change. Kind of weird with the boundary conditions, but solving for the other variable is different now. This is where things I guess start to get weird. This is an easy problem, but you can imagine. So let me write this out first. 3 solve for y. So let's write down what we know. We know our other equation is equal to this. I just moved that over to the other side. That other boundary condition that we were left with is this. We have to use it here. We still have one more left, but we're going to use that think of it as like a substitute for our initial condition, I guess. I don't really know the full explanation for it, but okay, we know this. Okay, this second order, we simply just solve the characteristic equation. That's imaginary, right? Plus minus lambda there. So now, and by the way, technically this should be lambda sub n. No, it doesn't matter. Yeah, no, it doesn't matter. And then once we get to this, actually, hold on one moment, because actually, no, we should be fine. There's some weird things. Laplace is very weird. Actually, no, we're good. I'm thinking of something else. We're gonna solve this the same way. So we're gonna just write out a characteristic equation. I'm gonna put it down here. That's C1 e to the n pi. That's what it was, right? N pi. It's all squared. Okay, no, actually, no. My suspicion was right. You see, so there's some weird things going on with lambda here. It has to become positive over here. It can't be imaginary. So if you come up here, you can see that this for lambda is always -0. So when we're solving for this, we have to already factor in the negative into the lambda. Okay, so really the trick is, that's how you can think about it. You have to plug in lambda before you continue to solve it. You're right, I don't know what I'm getting so confused about. We've done this in the past. You always have to plug in for lambda n first. I just always did it subconsciously. You always have to plug in for lambda n first. So then this would be n squared pi squared over a squared y. Solve the characteristic equation. R squared equals n squared pi squared over a squared. Take the square root. N pi over a plus minus, right? N pi over a. Write the general solution down, so it's just the change form for second order. That'd be little y. Right. Where was I? Okay, right here. So now right here, we basically want to solve for our constant. We can simplify it. So we can use our boundary condition. Which is equal to 0. Remember, this is y of little y, and then so C1 will be equal to negative C2. So then y is equal to negative C2 e to the n pi over a times y plus c2 e to the negative n pi y over a. So so basically we're going to do some tomfoolery here. Some little algebraic manipulation. I'm going to convert this into y of n. I'm going to pull out the c sub n. Let's pull out the negative c sub n, why not? E to the n pi over a times y minus e to the negative n pi y over a. Now, we're basically here, I think I have it paid. I think I have it here. Nope, I do not. Give me 1 second. I should have it right here. Yes. Okay. Sorry about that. Paste. Voila. Hyperbolic trig. So we can see, we're looking at this. This is equal to 2 sine of h. Well, not of x. Of n pi over a times y. So this is where it gets weird, you know. Now, in this exact moment here, basically, all that's going to happen here is just 2 and a cn are going to combine and create a new constant. So I like to call it cn prime. That's kind of weird, but that's the way it goes. And it's just, actually, so does the negative. The negative also goes into the cn. Now it's kind of a weird thing, but it's because it's a concrete number 2 and a concrete negative 1. We never dealt with this before in PDEs, so like previously we would have had something like c of n, like an e to the whatever for the t values, right? That's not a defined value because it depends on x. So it's not a defined value. So these are definite values. You can combine them with the cn. It's kind of weird. I mean, I think this has come up in calc and whatnot in the past. You should maybe be familiar with it. Now, the Fourier series is not much different. Okay. So it's really not much different. This is really where this changing stops. Well, I guess we're not really, because I mean, let's go to step 5 here. Sorry, step 4. Oh, let me do this first. I'm getting ahead of myself. Fundamental set of solutions and the general solution. U sub n is sine n pi over a. This one is times x because the other one was x of n. Yep. And then we have hyperbolic sine n pi over a times y. Then we can write, sorry, this is the general solution. Sum n equals 1 to infinity. Cn sine n pi over a times x times sinh n pi over a times y. And you can see, based off of this one, we have a Fourier sine series So that means it is odd. So then we would go ahead and solve for c sub n. What c sub n be? It's what I'm trying to remember off the dome here. 1 over L integral negative L to L, negative L to L f of x. In this case, it's g of x, I believe. Well, right. First of all, I kind of skipped this a bit. We should be on step 5 here. Fourier, oh sorry, well, I'm just going to call it Fourier series because we don't have an initial condition. Remember, this is the formula for C of n. I kind of skipped ahead. I skipped ahead. We're going to use the u of xb equals g of x as our initial condition. You can think of it as. That would just be, plugging in b for all of the y's. If this is a rectangle, these would cancel. A square, right? Because they're the same. This is the only difference for a square versus a rectangle is this step right here. The only difference. By the way. Yeah, then we find C of n. This is sine n pi. In this case, it would be this dx. Now, for this particular problem, it's going to be different because we have that cinch there. Whoa. We have that cinch there. That cinch is going to come over here with the g of x. Sorry, with the cn, not the gx. Because remember, we're solving for this and this together, not this. This is what goes over here, kind of. That should be an x there. There should be an x there. It is what goes there. Watch my derivation video on Fourier series coefficients. It'll all make sense. Yes, then we're left with this. Now, I know, well, first of all, what boundary is this on? Look at the boundary. 0 to a, right? 0 to a. Whoops. 0 to a. And, well, this is technically from, well, if you look at this one here, it's only from 0 to a, but we have to make it periodic. So let's figure this out. What is g of x? Well, it's an odd. Fourier sine series is odd. So then this is odd. So because our general solution denoted a odd series, g of x is an odd series. So this is odd. This is odd. And odd times an odd is an even. So what we can then do is go 2 over the length, which is a, from 0 to a. Right? Well, to be honest, a better explanation would be that we're making an even extension. I'm so sorry. it's going to be an odd extension on g of x. So I have made this mistake in the past where I did not explain this in my previous videos. I now regret. I'm too deep in. I'm not going back and redoing those videos. See, I caught a big mistake just right now. Like, I just clarified a massive thing for myself even. So what we're doing to make this work is we're making an odd extension on g of x to extend it into negative a, because essentially this summation up here that we have for your sine series is already being extended into negative a. I did not know that until right now, which is pretty cool. Everything makes more sense now. So now that we have established this confusion here, this g of x is being extended as being odd because of this. So we can get an even function, which then we can go from 0 to a, multiply it by 2. Voila. C to the n. I know part B says to use the g of x given, but we're going to ignore part B. We know how to do that. We know how to integrate. Right? That's the same thing. We know how to integrate. All you have to do is integrate this. You know how to do that. Then just solve for c sub n. It would end up in the form of this. Actually, let me just write out the solution. I'm going to keep it in integral form. We can pull out this 2 over a because it's a constant. N equals 1 to infinity. Integral 0 to a g of x sine n pi x over a over sinh n pi over a times b times sine of n pi x over a times sinh of n pi y over a. Alright, so I just plugged in c of n into our general solution. This is our final answer. Well, unless given a g of x, but I'm going to skip that part. So this was the case when we had This is the case when the top of the rectangle had a different temperature. But what if the bottom has a different temperature? So believe it or not, if the bottom, I'm sorry, not temperature, but like varying solution. Let's say the bottom was equal to g of x. It changes everything. It changes everything. Because now we're going to solve basically what's going to happen is when we separate the variables, well, actually the separation of variables will be the same, but our boundary condition, instead of being y of 0 is 0 for solving for y, it's going to be y of b equals 0, which greatly complicates things because you can't simply then say that c1 is equal to negative c2 and solve it easily like this. It's going to be very annoying to figure out. And it's one of the problems where a lot of confusion arises with this stuff, is when you have the bottom variable, bottom side is being equal to g of x or f of x, and all the other sides are 0. It's a very confusing case. So that will be the next video. And we have 3 more types after that, where we have a differing. We have a function on the top and the bottom, and I have another one with a full Newman problem with full Newman boundary conditions, all derivative boundary conditions. Then I have one of Robin, which is mixed between Dirichlet and Newman. So, and that's it. And then we'll move on to Laplace on a circular domain, semicircular domain. So I'll see you for those videos.